If you're into quantum computing, well then buckle up because today we are diving deep into a breakthrough that could change everything. Distributed quantum computing.
Yeah, this is big. Not just like a baby step forward, but more like a totally new way of thinking about how to build these super powerful machines.
Exactly. It feels like we've been hearing forever about this quantum revolution that's going to revolutionize everything, like medicine, materials, everything. The big question was always when? When will quantum computers be powerful enough to actually do all this crazy stuff? Well, when might actually be right now.
A team over at Oxford University might have just figured out how to make quantum computing practical, on a larger scale.
Okay, so before we go any further, let's make sure everyone's on the same page. Quantum computing, it's like it uses the crazy rules of the subatomic world to do calculations that would take regular computers, even supercomputers, millions of years to do.
And it all comes down to these things called qubits. You know how the bits in your computer can only be a 0 or a 1? Well, qubits can be both 0 and 1 at the same time. It's called superposition.
So it's kind of like a coin spinning in the air. It's both heads and tails until it lands. And that's what gives these quantum computers their power.
Yeah, that's a great way to think about it. Being able to be in multiple states at once, well, that's how quantum computers can tackle problems that would be impossible for regular computers, at least, in any reasonable amount of time.
We're talking about like cracking the codes that keep our online data safe, or designing totally new materials that have crazy properties,
Mm.
or even simulating the entire universe. I mean, the possibilities are pretty much endless.
But the big challenge has always been scalability. How do we build these quantum computers big enough and stable enough to handle these huge world-changing problems? People have been trying to cram more and more qubits onto a single chip, but it's really hard, and there are limits to how far you can push that.
Okay, so that's where this Oxford team comes in. Instead of trying to make one gigantic quantum computer, they've taken a page from traditional supercomputers.
Right. Supercomputers get their power by connecting lots of smaller computers together. So the Oxford team did the same thing, but with quantum computers. They created a network of smaller quantum modules.
So instead of one megacity trying to do everything, you have a bunch of smaller, specialized cities connected by superhighways, a network of quantum brains, basically.
And instead of using electrical connections, which can cause interference and heat problems at the quantum level, they used light.
Light.
Yeah. They're
Oh,
using photons, tiny particles of light, to send information between the modules.
okay. Light is fast, it's efficient, and we already use it to power the internet with fiber optic cables. That seems like a much more practical way to scale up quantum computing.
It is, and get this, the way they're using photons is even cooler. They're actually teleporting quantum gates between these modules.
Wait, hold on. Did you say teleportation? Like Star Trek teleportation? Is that even possible?
It might sound like science fiction, but quantum teleportation is a real thing. It's based on quantum entanglement, which, yeah, that's a whole other mind-bending concept.
Yeah. Okay, well, you have to explain entanglement now. I know it's like two particles are connected in a spooky way, but I don't really get the details.
Okay, so imagine you have two balls. One is red and one is blue, right? And they're linked so that they'll always show opposite colors. If you look at one and it's red, then you automatically know the other one's blue, even if they're miles apart. That's the basic idea behind entanglement.
Okay, I see. So in the quantum world, instead of colored balls, you have these entangled particles. But how does that let them teleport quantum gates?
Well, quantum gates are basically instructions that tell the qubits what to do. They're the building blocks of any quantum algorithm. The team at Oxford used entanglement to transfer the state of one particle to another particle in a different module. They basically teleported those instructions across the network.
So they don't actually move the particle, they just transfer its information to another particle that's already in the right place.
Exactly. And being able to teleport quantum information is huge. It means you can do calculations across this whole network of modules. It creates a system that's way more powerful than any single module could be on its own.
Okay, so they built this network, they're teleporting gates, but does it actually work?
So to test it out, they ran a classic quantum algorithm called Grover's algorithm. Think of it like trying to find a specific grain of sand on a beach. A normal computer would have to look at each grain one by one, but Grover's algorithm lets a quantum computer check multiple grains at the same time, making the search way faster.
So it's like having a million tiny helpers all looking for the grain of sand at once.
Exactly. And as you might expect, the distributed system ran the algorithm perfectly. They found their quantum needle in a haystack.
That's incredible. So they have a working proof of concept. This is a big deal,
Well,
right?
yeah. If you zoom out and look at the big picture, this isn't just about making bigger quantum computers. This distributed approach could be the foundation for a future quantum internet, a network that connects quantum computers all over the world.
Okay, now that sounds like something straight out of science fiction. What would a quantum internet even be like? And what could we actually do with it?
That's a great question, and it's definitely a whole other conversation. But before we get into that, let's take a closer look at the technology behind these linked-up quantum computers and how they actually work at a more basic level.
All right, so before we jump into this whole quantum internet thing, let's take a closer look at the tech behind these linked up quantum computers, like how they actually work at a more basic level.
Okay, yeah. You mentioned before they're using these trapped ions.
Yeah.
What are those exactly?
So trapped ions are basically individual atoms that have had an electron taken away. So that gives them a positive charge, right? And because they have this charge, scientists can use electromagnetic fields to, like, hold them in place. They're literally trapped in this vacuum chamber.
I see, okay. So we have these tiny atoms just floating in a vacuum. What happens then? This is where lasers come in. By pointing lasers at these trapped ions with like incredible precision, scientists can actually control their quantum state. They can put them into that superposition state we were talking about earlier.
So it's like the lasers are kind of like puppet masters controlling these trapped ions.
Exactly, I like that. And by carefully manipulating these ions with lasers, well, scientists can make them do these quantum logic operations.
And those are like,
They're the fundamental building blocks of quantum computing, just like logic gates are in a regular computer.
got it. Okay, so the lasers are controlling the ions, making them do these quantum computations. But how do they connect multiple modules together? That's where the photons come in, right?
Bingo. Photons are like the key to linking these trapped ion modules and letting them talk to each other. So this team at Oxford, they developed a special interface that allows photons to be sent between the modules. And those photons carry the quantum information.
So if I'm getting this right, they shine a laser at a trapped ion, and then that releases a photon that's carrying specific quantum information. That photon travels, like super fast, at the speed of light through a fiber optic cable to another module, and then it interacts with the trapped ion on the other end.
You got it. And the best part is that fiber optic cables, well, we already use them everywhere for the internet and communications. So this way of connecting quantum computers is super practical and scalable.
It's all making sense now, but I still have one big question. How does teleportation work? It still blows my mind a little bit.
Yeah, it is a crazy thing. And like we were saying before, it's all based on quantum entanglement. You remember those two colored balls that always have to be opposite colors? It's like that, but with particles.
Okay, right. So instead of physically moving the trapped ion, they use entanglement to transfer its quantum state, its information, to another ion in a different module. So it's like they're making a perfect copy of the ion's information and then sending that copy across the network.
Exactly. And remember those quantum gates, the ones that are being teleported. Well, those are basically the instructions for the quantum computer. So this teleportation process lets them send instructions across the whole network, which then lets them do complex calculations that use multiple modules.
So they're not teleporting Captain Kirk, but they are teleporting instructions for quantum algorithms.
Yeah. And this is what makes distributed quantum computing so powerful and flexible. You can have all these modules, each one specialized for different tasks, and by linking them together, you get this like quantum superbrain.
I see. So it's a pretty elegant way to solve that scaling up problem that's been holding quantum computing back.
Exactly. But there have to be some big challenges, right? I mean, quantum mechanics is notoriously difficult to work with.
Yeah, for sure. Nothing this groundbreaking is easy. So what are some of the biggest hurdles they've had to overcome?
Well, one of the biggest challenges in distributed quantum computing is keeping the quantum information safe as it's teleported between the modules, making sure it doesn't get messed up along the way.
Okay, and what does that mean, keeping it safe?
Think about it like making a copy of a document. If the copy is perfect, it has high fidelity. But if there are mistakes, well, the fidelity is low. And it's the same with quantum information. If the information gets messed up during teleportation, the calculation won't be accurate.
Ah, I see. So they have to make sure that the quantum information stays intact as it travels across the network. But why is that so hard?
It's hard because these quantum systems, they're incredibly sensitive to any kind of noise or interference, like even tiny vibrations or changes in temperature. they can mess up the quantum state and cause errors.
Wow, so it's like trying to send a message using a walkie-talkie during a hurricane. The signal's going to get all messed up because of everything else going on around it.
Perfect analogy. And that's why building these systems requires such extreme precision and control over every little detail.
So you don't just need the lasers and the trapped ions. You also need, like, perfectly engineered vacuum chambers, super stable optical fibers, and all kinds of error correction techniques. It's got to be incredibly complicated.
It is. It's a huge team effort involving physicists, engineers, computer scientists, and a whole bunch of other people.
Okay, so it's super exciting, but it sounds like we're still in the early days of distributed quantum computing. There's still a lot of work to be done before we see these things everywhere, right?
Definitely. But the progress they're making is really impressive. And with each new breakthrough, like this one from Oxford, we get closer and closer to really unlocking the power of quantum computing.
It's been so cool learning about the technology behind all this, but the big question is, what can we actually do with it? Like, what are the real implications of a global network of these super powerful computers?
Yeah, that's the big question. And it's a conversation that deserves way more time. So let's move on to the next part and talk about the incredible potential of this quantum revolution and how it might just change the world as we know it.
Okay, so we've spent this whole episode talking about the how of distributed quantum computing. You know, the trapped ions, the teleportation, all that mind-blowing engineering.
Yeah.
But now let's talk about the why. What's the point?
Right.
What kind of future does this tech actually unlock?
Well, the potential applications of a global quantum computing network are pretty much limitless. It's like we've given humanity this brand new set of keys to the universe, and we're just starting to figure out what they can unlock.
Okay, so where do we even begin? What are some of the areas where we might see a real-world impact?
One of the most exciting areas is medicine. Imagine being able to design drugs so precise that they only target specific diseases at like the molecular level. So you'd have way fewer side effects and the drugs would be way more effective.
That sounds incredible, like true personalized medicine where you can create treatments based on a person's genes.
Exactly. And with quantum computers, we could actually simulate how molecules interact in a way that's just impossible with normal computers. I mean, we could revolutionize drug discovery and maybe even find cures for diseases like cancer and Alzheimer's.
Wow, that's amazing. Okay, but besides medicine, what else could this technology change?
Material science is another area that could be totally disrupted. Quantum computers could help us design completely new materials that have properties we can't even imagine right now.
Like super strong, but super lightweight materials for spacecraft. Or materials that can repair themselves, like Wolverine.
Yeah.
Stuff like that.
No, and it goes way beyond just those examples. We could change entire industries, aerospace, construction, electronics, everything by making materials that are perfectly suited for their jobs.
Speaking of sci-fi, we got to talk about the quantum internet. What kind of possibilities does a quantum internet open up?
Well, the quantum internet would totally change how we think about communication. It could mean truly secure communication, where it's basically impossible to hack or eavesdrop. And the level of connection we could have globally, it's hard to even imagine right now.
So basically, hacking and data breaches would be a thing of the past.
It's possible. The laws of quantum mechanics, well, they make it almost impossible to intercept information sent over a quantum network. That'll be huge for governments, businesses, and even regular people.
And it's not just about security, right? A quantum internet could also, like, turbocharge scientific collaboration.
Absolutely. Imagine scientists all over the world working together on these super complex simulations and experiments, all in real time. It wouldn't matter where they were physically. It'd be like they were all in the same lab.
It's like one giant global brainstorming session powered by quantum entanglement. Who knows what kind of breakthroughs we could see from that?
Yeah, it's pretty mind-blowing. And these are just a few examples. We might even see quantum computers revolutionizing artificial intelligence, financial modeling, weather forecasting, really anything that needs a ton of computing power and data analysis.
It sounds like we're on the edge of this huge technological revolution. And it could change everything.
Yeah, for sure. And it's super exciting to be alive to see all of this happening. But we do have to remember that we're still in the very early stages.
Right, so no quantum flying cars just yet.
Probably not anytime soon. But with every new breakthrough, like the one we've been talking about today, we get closer and closer to reaching the full potential of this field.
It's definitely a future worth working towards. And it's clear that quantum computing will be a huge part of shaping that future. Thanks for breaking all of this down for us. I think it's safe to say we'll all be watching this space very closely as things continue to develop.
The quantum world is full of surprises. It really makes us rethink what's possible. Who knows what incredible discoveries are just waiting to be found?
That's a great point, and a great place to wrap things up. Thanks for joining us on this journey into the mind-bending world of distributed quantum computing. Until next time, keep exploring, keep asking questions, and keep diving deep.